You type a prompt into a text box, and seconds later, a perfectly formed, highly intelligent answer appears. But if someone asked you right now to draw exactly what happens inside that black box to produce those words, most people would completely freeze. Today, this explainer fixes that. By the end of this, you'll be able to map out the internal architecture of text generation from memory. Let's dive in.
Look at this quote from Cola's blog. Backpropagation can make training deep models 10 million times faster. 10 million! Just think about what that actually means. It's a mathematical trick that literally turns what would take 200,000 years of computing time into just one single week. That is the monumental scale of the engineering we're dealing with here.
Welcome to the explainer. I'm absolutely thrilled you're here because we are going on a really fascinating journey today. We're zooming way in, past all the hype, past the slick user interfaces, and looking straight under the hood of modern AI to break down the exact mathematics that make these systems tick. Here is our roadmap for today. 1. The deep learning hierarchy. 2. The engine, backpropagation. 3. The breakthrough, transformers. 4. Understanding context and position. And finally, 5. The inference process.
All right, let's kick things off with Section 1, the deep learning hierarchy.
Let's clear up some terms that everyone uses but very few actually understand. Traditional machine learning, that requires humans to intervene. We explicitly have to tell the algorithm what features to look for in the data. But deep learning uses artificial neural networks with 4 or more layers, and that depth is a total game changer. It extracts features entirely automatically. It figures out the hierarchical patterns on its own, which is incredibly powerful, but as a trade-off, it has a massive dependency on high-end GPUs to do the heavy mathematical lifting.
Section 2. The engine, backpropagation.
So how do those deep layers actually learn anything without us holding their hand? It's all about an iterative control loop. Step 1. The network feeds data forward to make a prediction. Step 2. It calculates the loss, which is basically measuring exactly how wrong that prediction was compared to reality. Step 3. It works backward to adjust the millions of weights and biases connecting its artificial neurons. It's just this endless loop of predicting, measuring failure, and correcting itself.
But here's the catch. Calculating how much every single one of those millions of weights contributed to the error, that's a combinatorial nightmare. If you calculate every path individually, the math explodes exponentially. So engineers use a brilliant technique called reverse mode differentiation, or backpropagation. By starting at the output and moving backward, it merges paths at every node to avoid doing the same math twice. It computes derivatives for millions of parameters in one fell swoop. It is unintuitively cheap, and honestly, it's the only reason deep learning is even possible today.
Section 3. The breakthrough, transformers.
Knowing how to learn is one thing, but how do we structure the brain of a modern language model? Well, the 4 transformers, AI read text sequentially, one word after another. Huge bottleneck. Transformers process everything in parallel, using a mechanism called self-attention, driven by a query, key, and value system. Think of it like a database search happening inside a sentence. The query is the current word asking for context. It checks the keys, the labels of all the other words. When it finds a strong match, it absorbs the value, the actual meaning of that associated word. That's how it instantly knows that in the phrase, the capital of France, the word capital strongly relates to France.
Section 4. Understanding context and position.
But wait, this creates a massive information gap. If a transformer reads every single word in a sentence at the exact same time in parallel, how does it know the order of the words? How does it know the cat ate the mouse isn't the mouse ate the cat? The answer is mathematically beautiful. It's called rotary position embedding, or ROPE. Imagine a clock face. Instead of stamping an absolute number onto a word, ROPE rotates the word's mathematical vector based on its position. So the distance between 2 words is simply the angle between their hands on the clock. Position 2 and 6 have the exact same angle as position 100 and 104. The AI natively understands relative distance, and amazingly, it does this with literally 0 extra parameters to train.
Section 5. The inference process. Now for the grand finale. We have a parallel processing transformer that natively understands context and position. How do we actually generate the text you see on your screen? It operates like an assembly line with 2 distinct phases. First is the prefill phase. The AI reads your entire prompt all at once, in parallel, building that rich web of attention we just talked about. Second is the decode phase. This is where it switches gears and goes auto-regressive, typing out the answer just one single token or chunk of a word at a time, constantly looking back at what it just wrote to figure out what comes next.
But generating one word at a time requires the model to constantly rethink the whole sentence, which is terribly slow. To fix this, engineers use KV caching. By storing the intermediate key and value calculations of the words it has already processed, the AI doesn't have to recalculate the past for every new word. It is a massive speed boost. But the trade-off? It consumes incredibly high amounts of your GPU's memory. You are literally trading your VRAM footprint for text generation speed. At the very end of this decode loop, the model spits out raw numbers called logits. These are mathematically transformed into a probability distribution. If your prompt is, "The capital of France is," the model doesn't just know the answer. It calculates that Paris has an 85% probability of being the next word, Lyon is 10%, and others make up 5%. Based on your settings, it picks a token, prints it to your screen, feeds it back into the start of the loop, and the whole process repeats until the thought is complete.
And that brings us to our final thought. We've seen how elegant the math is, from backpropagation to rotary embeddings. But as we push these context windows from a few thousand words to literally millions of tokens, we are hitting a physical wall of memory and compute. How will the limits of our silicon hardware force us to fundamentally redesign the next generation of AI architecture? It is the absolute frontier of modern technology. Now, I want to hear from you. Drop in the comments which component of this architecture surprised you the most. I read every single one. Keep learning, and I'll catch you in the next explainer.